You drive over it every single day. You don't think about it. Your tires touch it, your commute depends on it, and you have never once asked what's underneath it. But the road under your car is not just a slab of black rock. It's a 50-year science experiment, and right now, it's either winning or losing. Some roads last 2 decades without a single crack. Others fall apart in 18 months. Same material, same black surface, same painted lines. So why does one hold up like a fortress while the other crumbles like stale bread? The answer isn't the asphalt you can see. It's everything you can't. Start with what a road actually is. Not a single layer, but a stack. For layers, usually. At the bottom, the subgrade, just compacted native soil, the ground itself, reshaped and packed down. Above that, a layer of crushed stone called the subbase. Above that, the base course, more crushed stone, but finer and stronger. And only at the very top, that thin black skin you're used to seeing, the surface course, sometimes barely 3 inches thick. Here's the part that surprises people. That thin black top layer isn't what holds your car up. The layers underneath are doing almost all the work. Think of asphalt like the icing on a cake. It looks like the whole thing. It's really just the finish. So if the icing isn't the strength, what is? Compaction. 90% of a road's future depends on how tightly those lower layers were packed before a single drop of asphalt touched them. And this is where most road failures actually begin, not years later, but on day one, in ground nobody can see again once it's paved over. Picture a construction crew running a vibratory roller, a machine that looks like a giant metal drum, back and forth across loose crushed stone. That vibration isn't for show. It's shaking the individual rock particles into the tightest possible arrangement, squeezing out air pockets one pass at a time. Engineers measure the result with something called a nuclear density gauge, a handheld device that reads how tightly packed the soil actually is, expressed as a percentage of its theoretical maximum density. Most specifications demand at least 95%. Fall short of that number, even by a little, and you've built a road on a foundation with hidden air pockets, gaps that will slowly collapse under the weight of traffic for years afterward. And here's the unsettling part. Nobody driving over that road will ever see the shortcut. The surface goes down smooth. The paint goes on fresh. The failure is already sitting there, buried, waiting. In 1958, the American Association of State Highway Officials ran one of the largest engineering experiments in American history. It's called the AASHO Road Test. And if you've ever wondered why some highways survive semi-trucks for decades while others buckle under regular traffic, this is where the answer comes from. Researchers built real roads in Illinois, then drove thousands of trucks over them, over and over, cataloging exactly how and when each section failed. What they found changed how every road on Earth gets built. A single heavily loaded truck axle does roughly the same damage as 10,000 cars. Not 10, not 100, 10,000. That number has a name now, the fourth power law, because road damage scales with the fourth power of axle weight. Double the weight on a truck, and you don't double the damage. You multiply it by 16. Suddenly the cracked road outside your house makes a lot more sense. It's not that the road was built badly. It's that engineers underestimated exactly how much heavier trucks would get, or exactly how much traffic would actually roll across it, decade after decade. But weight isn't the only enemy. Water is worse. Asphalt isn't solid the way it looks. Under a microscope, it's full of tiny air voids, gaps between the stone and the binder that holds it together. Water finds those gaps. And when water gets underneath a road and then freezes, it expands. Ice takes up about 9% more space than liquid water. That expansion pushes upward, cracks the layers apart from below, and repeats every single winter until the road looks like shattered glass. This is called the freeze-thaw cycle, and it explains something you've probably noticed without realizing it. Roads in Arizona often last far longer than roads in Michigan, even with identical traffic. It's not the sun wearing them down first. It's the water hiding underneath, freezing and thawing, working the road apart from the inside. There's a specific version of this that engineers call frost heave, and it can lift an entire section of pavement several inches off the ground overnight. Water trapped in the base layers freezes into thin ice lenses, sheets of ice that grow by pulling in more moisture from the surrounding soil as the temperature drops. Layer by layer, those ice lenses stack up, pushing the road surface upward like a slow-motion explosion. Come spring, the ice melts, the support vanishes instantly, and the road drops back down. Except now it's sitting on saturated, weakened soil instead of solid ground. Drive over that same stretch in April, right after a thaw, and you'll feel the road flex slightly under your tires. That's not your imagination. That's the ground beneath you, still soft from winter, still recovering from being frozen and thawed in place. There's a researcher named Carl Monesmith, an engineer at UC Berkeley, who spent much of his career studying exactly how pavement fails under repeated stress, not from one giant load, but from millions of small, ordinary ones. His work helped explain something that sounds almost poetic for an engineering finding. Roads don't usually fail from one dramatic event. They fail from fatigue. The same story as a paperclip bent back and forth until it snaps. Every car that crosses a road bends it, microscopically, invisibly, and after enough bends, cracks appear where there was once a smooth black surface. So now you know two of the enemies. Wait, water. There's a third, and it's the one nobody blames enough, the binder itself. Asphalt binder is essentially a byproduct of crude oil refining, and it behaves strangely depending on temperature. In extreme heat, it can turn soft and start to flow, letting truck tires push ruts straight into the surface. In extreme cold, that same binder can turn brittle, almost glass-like, and crack under the slightest stress. Engineers needed a binder that could survive both conditions in the same year, sometimes the same week. That problem led to a research program in the late 1980s called the Strategic Highway Research Program, which eventually produced something known as Superpave, a performance-based grading system for asphalt binder. Instead of picking asphalt off a shelf, engineers now select a binder graded for the exact climate of the road it's going into. A road in Minnesota gets a binder engineered to stay flexible at -30 degrees. A road in Texas gets one engineered to resist flowing at 120. Use the wrong grade. Save a little money up front, and you've built a road that's already failing before the first car drives on it. This is the part almost nobody outside civil engineering knows. A road that cracks in 2 years usually wasn't cheaply built by accident. It was often cheaply built on purpose. The wrong binder for the climate, under-compacted base layers, or drainage that was never properly designed, all invisible the day the road opens, all catastrophic 5 winters later. Drainage might be the most underrated factor of all. A road with nowhere for water to go is a road with a short lifespan, no matter how expensive the asphalt on top of it was. Engineers design crown slopes, subtle curves across the road's width, so rain sheds off to the sides instead of pooling. They install underdrains, buried perforated pipes that pull groundwater away from the base layers before it can freeze and heave. Skip that step, and even a perfectly mixed, perfectly graded asphalt surface will fail early because the damage isn't happening on top. It's happening underneath, where nobody's checking. You can actually see drainage failure happening in real time, if you know what to look for. Alligator cracking, a web of interlocking cracks that looks exactly like reptile skin, almost always starts in a spot where water has been sitting underneath the surface for months, softening the base layer until it can no longer support the weight above it. Once that pattern appears, the road isn't just wearing out. It's actively failing, because the individual pieces of asphalt inside that cracked web have lost the support they need and started rocking independently under every passing tire, grinding themselves apart from below. Even the shoulders of a road matter more than most people assume. A shoulder that's lower than the driving lane, even by an inch, becomes a channel funneling water straight back toward the pavement edge instead of away from it. Multiply that by a few thousand rainstorms over a decade, and a road that was engineered correctly in the center can still fail first along its edges, exactly where the water had somewhere convenient to collect. Put it all together, and the 20-year road and the 2-year road stop looking like the same kind of object. The 20-year road had its subgrade properly compacted, tested with tools that measure density down to the percentage point. It had a binder graded for its exact climate, not just whatever was cheapest that quarter. It had drainage engineered before the first truck of asphalt ever arrived. And it was built to a specific traffic estimate, accounting for the fourth power law, so it wouldn't collapse the moment freight traffic increased. The 2-year road skipped one of those steps, maybe more than one, and you'd never know it by looking, because for the first few months, both roads look identical. Same black surface, same fresh paint, The failure is already built in, it just hasn't shown up yet. There's something almost unsettling about that. Every road you drive on today is either quietly winning a 50-year war against water, weight, and temperature, or quietly losing one, and there's no way to tell just by looking at the surface. The real story is buried under your tires, in layers you'll never see, decided by decisions made before the asphalt truck even arrived on site. So next time you hit a pothole and curse the city for it, remember what's really going on beneath you. It's not bad luck. It's not just wear and tear. It's physics, the fourth power law, the freeze-thaw cycle, a binder graded for the wrong climate, playing out exactly as predicted, inch by inch, winter by winter, until the surface finally gives up the secret that was written into the ground the whole time. You drive over it every single day. Now you know exactly what you're driving on.